Hello, ladies and gentlemen. Welcome to another exciting event of One Quantum Philippines. The title is Using Google Collaboratory for Scientific Computing. We are One Quantum Philippines, and our mission is to make quantum computing accessible to the Filipino people and introducing quantum computing as early as possible to a child's education. So our guest speaker here is a member of One Quantum Philippines. His name is Engineer Dylan Josh Lopez. He is currently a research assistant in the Intelligent Power Systems and Energy Lab at Chungyuan Christian University. He finished his bachelor's degree in computer engineering at Adamson University, Manila, Philippines, and his master's degree in computer science and information engineering, majoring in intelligent software design at Tsinghua University in Hsinchu, Taiwan, and is currently pursuing his PhD in electrical engineering at Chungyuan Christian University in Taoyuan, Taiwan. Currently, he is the Chief Innovation Officer at Borg Technologies, a startup in the Philippines. He has several years of experience in teaching artificial intelligence, data analytics, intellectual property, and technopreneurship in the Philippines. His current research focuses on optimization of power systems using hybrid classical quantum computing artificial intelligence. He also has researches on artificial intelligence and data science for sustainability, computer vision, and ubiquitous systems, wherein he has produced several publications and patents. Engineer Lopez is a certified research and development project manager, accredited by the American Project Management Association, a certified computer engineer in the Philippines, an associate member of the National Research Council of the Philippines, a member of the Talent Development Council of the Analytics Association of the Philippines, a professional member of the Institute of Electrical and Electronics Engineers, an honorary member of the Phi Tau Phi Scholastic Honor Society of the Republic of China in Taiwan. And most of all, he is a proud member of One Quantum Philippines. So, ladies and gentlemen, I give you Dylan.
All
The
right. Hello,
podium is
everybody.
yours.
So, good evening. Yeah, it's already a bit of an evening. So, yeah, my screen's a bit flashing though, but don't worry. Okay. So, thank you, Sir Bobby. Thank you, One Quantum, and everyone watching today. And we'll be talking about a very interesting topic for those who are new to the field or, already into the field, but want to move into a new direction. All right. So, for those who have epileptic uh, tendencies, I'll stop my camera for a moment. Yeah, sorry. Okay. So, I'll be sharing my presentation. Don't worry, it'll be a very short presentation, and we're going to focus more on activities later on. Right. Let me just share my screen here. Mhm. All right, just find that. for a moment. Right. Okay, so I hope you can see my screen right now. Okay. So, all right, welcome. And we're going to talk about Google Collaboratory for scientific computing. So, welcome again to our talk for tonight. Okay, so so if you're here, so this talk is for everyone that who likes to simulate science through software. You may be programmers who want to dwell on scientific and computational programming, or you already have done scientific computing, but you want to try something new, or you are required by your supervisors, advisors, professors to use Google Colab or do it scientific computing. Maybe you're just curious, or maybe you're just really bored. But if you're here, thank you, and I hope you can get something from this. Okay, so for this talk, we are going to talk about, of course, Google Colab, the workspace, a bit of a Python speedrun for those who have not yet encountered Python, a bit of linear algebra, graphs, plots, and some of the favorite math I do in Google Colab. Probably something that you have interest in as well. But yeah, we can try other things as well in a Google Colab. And don't worry, some topics might be too hard. Some topics might be too easy for some people here, but that's fine. If you have anything that you want us to cover, just send us a message, and maybe we can cover it in the next video or the next engagement. All right. So actually, I'm already done with a bit of my slides here. So I hope you can get to the following links I have here. So the first link on your left, it would be the Google Colab home. So you can try for yourself what is Google Colab, what are you going to do with Google Colab, get a bit of a feel about it. And today's activity is on the right. So this will lead you to the Google Colab that we have prepared for you, so you can run as we go through the talk. Okay, so yeah, this is already my last slide, and we'll go ahead with the Google Colab that we prepared for you. Right, so maybe I'll give you a bit of 15 seconds to maybe save these or um, get go to the links here. Right. Right. So I think you're done with that. I hope you are. But anyway, don't worry if you don't have the links yet. We're going to post them later again. So yeah, I think that's it for the presentation. And we'll go ahead to the Google Colab. Okay, let me just go back to our stream here. Okay. All right. So, okay. So let's move on to the Google Colab. So let me just get to that part. Okay, let's go to. All right, here it is. Okay, now I hope you're seeing my tab already. So we're going to have several parts in this talk. So we're going to talk about, of course, Google Colab, scientific computing, and all of the cool maths that we can do with Google Colab. All right, so first, you might not be familiar with scientific computing. That's completely okay. We're going to go through some of it of the mathematics going on, but most probably you're not familiar with Google Colab. So let's try to go to what's ever in the screen right now. All right, on the top, you might be seeing the name of the file I have right here. That's cool. And you can save whatever you do in GitHub, by the way. So that's great. So, mhm. So I'll teach you later probably in how you would like to save this in your GitHub. But for now, let's check on the what functionalities that we could find in your notebooks right here. Now, if you are familiar with IPython notebooks or IPYNB, use Jupyter Notebook, this is going to be a bit of a breeze for you. So you're just going to have the feel of working with Jupyter Notebook online. So a good advantage of Google Colab with Jupyter is that you can do this not on a local machine. That means you don't have to use your just one laptop. You have data on you have your notebook on one laptop, and you want to work on another laptop or computer, and you want to get that file. You want to send that. That's gonna be a bit of a hassle for most of you. Google Colab works on the cloud. That means you're working on Google servers. So if you're working on one computer right now, you can now just share this file or access it in their with your Google Drive on another machine. So that's going to be great. Since yeah, its name is Colab, that means it's for collaboration. That means you can share this file to your friends, your colleagues, so that they could see the algorithms that you're doing, the prototypes that you're working on, and that'll be great. So how do you do that? So there's a share button right here. So you can share this to other people. You can click this. I think it's going to be a bit different for you. If you click on the share here, you can share access to people as viewers, as editors, just like what you would do on your regular Google Docs. So that's going to be great. You can even create your comments in here and even check the versions. That's also going to be great for those who have experience with version control. Right. So here I have file. You can view this on GitHub. That's cool. You can even add notebooks. You have your own IPython notebook uploaded here. That's great. You can create your own notebook as well if you want to create a new activity. Open an existing notebook in your Google Drive. You can upload notebooks, again, from your IPYNBs. You can save this in GitHub. You save a copy in GitHub. That's also a very good functionality. You are opening your Google Colab, then just save that into a repo. That's going to be great. Bro, so there's also revision history if you want to see how are the changes from one time to another. Maybe you missed a variable, you have missed a simulation, you want to go back for a few days. That's also going to be possible. Also, if your advisor, professor, or boss would require you to send IPYNBs, that's also going to be okay. So you can just create something in Colab, and you can just download this as either an IPYNB file or Jupyter Notebook file or a Python file, and that's going to be okay. So others here might be too much for now, but I'll go to the interesting part. So edit. So you can edit the cells right here. By the way, cells are things here that the rectangles that you might be clicking on, those are cells. So you can click on them to make some code, or you can make some text. That is what you call markdowns. And don't worry, we're going to talk about that more later on. Okay, so here we also have runtime, and just another interesting feature of Google Colab. So you can go down and look at change runtime. Maybe if you can't see uh, the drop downs here, that's okay. Just click on runtime and you'll see change runtime type. Now, if you have a change runtime type, you might not see what's on my tab, but that's okay. There is what we call a hardware accelerator. Now, if you click the drop down right there, you have none, GPU, and TPU. Now, for those who are practicing AI, this is something that you might be fangirling about, right? So if you choose none, this is just running a regular CPU on a Google Cloud server. Now, if you click on the GPU, you can access the GPU on that cloud server in Google, and also a tensor processing unit for those who are specific with running AI on tensors. But again, we're not going to talk about AI much today. But if you are practicing AI and you want to transition to Google Colab, this is going to be great for you. All right, so I'm not going to select any GPUs or anything. We're just going to use CPUs for today. All right. So let's look on your left. So these are some options. So you can you can hover on the first button on the top. It's just the table of contents. So you can see a lot of things right here. Now, these are the sections that we prepared of this notebook. So you can just click on those and it can redirect to you it can redirect you to whichever parts in the notebook that you are working on. There's also a find and replace. So this is something that is also cool if you want to change something in your code, especially want to change a variable. So you can find and replace something right here. You also have snippets under that, or rather, just first variables. So you can we can check on this later since we're not running on any variables just yet. So once we run this, that means you can track the values of the variables that you have currently on the notebook, and that's going to be great. And lastly, we have files. Now, if you're working on data sets, you're saving data, you save a picture, a graph, or any type of data within Google Colab. Since this is just an instance in the cloud, that means it's temporary, it's transient. So whatever you're saving here or uploading, it will be gone after probably 12 hours or when the instance is already shut down, if it detects that you're not working on anything anymore. So you got to be aware of that. So you probably need to download everything that you have right here. Now, there are techniques that it could automatically save in your Google Drive, but that's for another day probably. But yeah, that's possible. Don't worry. So here, you can just upload or download your files, whatever you're working on. So that's cool. Now, you might notice once you have clicked this file right here, although it's already done with mine, you were connected to the file, or rather, you're connected to the server. So it's going to load and show that you're connecting, initialize, and you're being connected. And you can see here there's RAM and disk. So this signifies that you are now connected to the Google Cloud. All right. So that's cool. Now, we are now going to each of the parts of Google Colab. So I think I already covered most of that for part one. So I already know what is Google Colab. It is very, very similar to Jupyter Notebook. Instead, it's running on the cloud instead of your local host. Right? So here we have cells. So the workspace in Google Colab consists of cells. So there are two types of cells in Google Colab. So there are text cells or our markdown cell. So you can double click on whatever here. So you can double click in this one, and you can see you can even type whatever you want here. Now, this is something that you might talk about more later. If you are more on the physics or science side, yes, it supports latex, sorry, or LaTeX, or whatever what you're comfortable with. So yeah, you can create your documentations here. You can set links. You can put even images in a markdown cell. If you want to discuss a certain algorithm, a certain piece of formula, you can do that here. And you're going to see that maybe later on once we have discussed the functions. And don't worry, we're going to work on that. But here you can put emojis if you want. You can put numbers, items, or even, yeah, piece of code. So I'm not going to go gung ho with this anyway. But yeah, you can explore a markdown cell. You can put this as part of a comment or documentation, especially if you want to explain something to someone else with your collab. Now, for those who are educators out here, this is going to be a great tool to explain lessons. So if you want to explain theory as well as the application of your code, this is something that you might want to look into. So what I do when I teach, computational thinking or maybe basic linear algebra with programming, this is a great way to show them the theory while reading and applying it right away, which is something that you can do with the code cell. Now, is the code cell. Now, you might notice that it's very different. So a code cell, you can just do one click and you can, write code. So how do you add one though? So you can go at the edge of your cells. Right here is the edge. So you can add code or text, whichever you want, above or below. Okay. So here we have a code cell. Now, just like any type of IPython notebook, you can just type whatever you want and it could run. Now, right here, you know that this, for those who know Python, this is what we call a multi-line text, or just a doc string, a multi-line comment rather, or a doc string for those who are really familiar with it. So you can type whatever you want here. You can declare variables. We can do that later though. And yeah, you can let's type, for example, x is equals to 1. You can do y is equal to 2, and and that would run. And ways to run that, you can press the play button right here, or there are shortcuts such as Control Enter or Shift Enter. That's going to be okay. Whatever you're comfortable with, that's great. Right. So right now, oh yeah, I'd like to show you there are variables here. So if we check here, you see there is a variable x and y, and the type is int. Now you might be curious what a shape. What's a shape? So is a bit specific and we're working with vectors. So if you're familiar with linear algebra, yes, you can simulate them here or even programmatically encode a, for example, a linear equation here and work with it. And yeah, we're going to talk about that later. Okay. So next would be some comments and documentation. So there, again, we have these three dots, right? Three quotes right here. That's a doc string. So if you would, for example, I'll create one here. If I'm going to create, I'm going to press the single quotes 3 times, 1, 2, 3, and press enter. And that's going to start a doc string. So this is a doc string again. And I'm going to close that with another 3 quotes. So that's already a doc string that we're going to work with, right? So I'm just going to delete this since it's already done here. So when you run this, it doesn't really do anything since, yeah, it's just a piece of text. So if you add something like x is equal to 0, this should not appear since it's now focusing on the code. Now you can do comments with a single hashtag or a sharp. So you can do that. You can even add another one to have a bit more complex code. That's cool. So yeah, so you can now work with more code cells and markdown cells in the next part. Now, for those who are not familiar with Python, I'm sorry, this is going to be a bit fast. For those who are already know Python, this might be too easy for you or too slow. Right. So let's try a bit of simple codes in Python. Now, if you have experience with MATLAB, most probably MATLAB if you're doing scientific computing, or C++ if you're a seasoned programmer, you might be you might experience a bit of a culture shock here, but that's going to be okay. Again, programming takes practice. Right. So let's play a print. So I'm going to print, I'm going to type here print. So it's already hit there. Anyway, so you can do a print function, and inside here, you can create a string. So whatever inside, you can do a print, you can print it. So let's do the very basic thing. So I'm going to delete my name here. Hello world. So just going to print hello world. Remember, if you're going to print a string and close it with double quotes. Okay. So you can run this using Control Enter. I'm going to use Control Enter. You can press the play button. That's cool as well, or Shift Enter. I'm going to do a Control Enter. So I'm going to hit Control and press Enter. And right here below is the output of that cell, which is going to print hello world. Now I can print numbers as well. So I can print 1. And I can do 1 plus 1. So, right? And you can even print your name. So you can, so hi, my name is whatever your name would be. My name is Dylan. So I'm going to print that here. So that's easy. That's a very easy print function. Now for those who have not yet done Python, now you have known the print function. Now you can just run this again and again. Right. Oh, just a piece of advice that these cells are not individual programs. These cells are all connected to one another. You're just, playing one point in time, especially for those who know Jupyter notebooks. You are working with a whole file. That means the continuum of the cells does not stop with one cell. It just continues whatever cell you're playing. Cool. Next would be variable declarations. Now, there could be numerical and non-numerical variables in Python. And unlike with C++ that you have to declare the data type beforehand, here Python just automatically does that for you. So for example, I'm going to create a num float. So the variable I have here is num float, and I'm going to declare 1.0, and that's going to be automatically a float. Python knows that. You can also input an integer and a complex number. Okay, I'm going to run that, and let's see. So we can check the num int using a type function. So you can type and enclose in the parentheses as a parameter. You can put num or whatever variable you want to check. And you can see it's an int. So Python knows that you have stored inside the numInt variable. So that's cool. So we'll get to the complex number right here in a bit, so don't worry. Okay. So float, you can check that it is a float, a num float. And oh, well, let's check here inside the let's have another one here. I didn't put the complex, but anyway, let's put another code here and let's check. How about num complex? And see, it's the type is complex. Now, you might be a bit shocked here that I'm not printing anything, but there's something out there. This is something that you can observe with Jupyter Notebooks and as well with Google Colab. If the last thing that you put right here in a cell is a variable or something that could be displayed, Jupyter Notebook or yeah, generally Google Colab can display that for you at the last part. So here, if I put type num int, it's gonna display whatever is inside or what's the result of type num int. So it's the same if I do a print. So it's gonna be also cool. So it shows it's a class int. Now, what if I did this? So if I did something, I overwrite the last part of the cell. So using that logic, so the last part of the cell would be a type num complex. So it's only going to print the last part right here. So it's complex. It did not print num int. Now, if you want to see both, you need to print them, put them inside a print function. Okay. Let's just print that. And voila. There. So just keep in mind that only the last part of the cell would be shown. So if you want to print a lot of things, you need to print it or display it using a print function. All right, cool. So we're done with the numerical variables. So we're not going to talk about the arithmetic yet. So just don't worry about it. We're going to discuss it a bit in a while. Okay. So non-numerical variables. So these could be strings. Although Booleans are also yes numerical in a sense, but in this case, it's going to be a bit of a categorical type of variable. So it's a bit of non-numerical, but you can debate that it can be numerical as well. But yeah, for the sake of this discussion, let's just say it's non-numerical as of the moment. Okay, so a Boolean value, a variable, and a string. Okay, so we have a string here, and we can print what's inside that variable. It could be a string, of course, it's a string, and we can print the type of the string. Okay, so it's a class of a string or str. Now we can do let's print. We can print here the num and a string. Okay. So the num int here is 2. That's the variable that we had earlier, and the string here is our variable right here. So you can print two things at the same time. So that's also cool. Now, we already done something like this. So we can now also convert strings to integers. So for those who are familiar with conversion or polymorphism, this is it in Python. So you can just cast a string right here, string num. So cast is a term, by the way, that converts a string to a number. So that's casting or parsing for more specific. So we can parse a string here, a number string, which is string num is declared as 1. Oh, I'm going to run this. Yeah, string num is quote unquote 1. So that's a string of a 1. So you can't perform any arithmetic with a string. So yeah. So you need to convert that. So we can do int of a string num, and that will print the type of int. Oh, see right here. Okay, cool. Now let's print the Boolean. The Boolean values again could any are binary variables. So these are Boolean, true or false. So the value for Boolean here is true. So yeah, okay, that's cool. And the type is bool. Okay, so let's do a bit of an operation though. You can do a not bool. So this is just a spoiler for Boolean values because we're not going to cover a Boolean value variables here or Boolean operations. So I'm sorry about that. We're going to do a bit of an overview about it, but yeah. But here, not and or exists. So Boolean operations do exist in Python as well. So that's cool. So we can do not and of course any other Boolean operations. So again, still the type would be Boolean. Now, we can also convert Booleans into strings. So here we have a string value of a string Boolean. The type here is a string. So if we want to print, okay, I'm just going to comment this out and print the string value. So it's still true, but it is a string. Okay, cool. So yeah, normally I was supposed to ask you if you have any questions out of habit, but anyway, if you do have questions, please leave them in the comments, and we're gonna get to that later. Cool. So next we're gonna do a bit of arithmetic and logical operations, right? So let's declare some numbers and do some math. So slowly but surely we are getting to the scientific computation part. So here we can just have your variables, declare them as your integers of 80 and 90 right here. And, oh, there's something new. This is what we call an F string. So an F string is a type of a string which you can format. So how does that work? So normally you have a string right here enclosed with the single quote, double quote, doesn't matter in Python. So both there's no difference actually, so that's completely fine. It's just your convention or your company's convention with it, whichever would be best. But if you're, a bit of a C++ purist, you may use, single quotes for constant or single characters or double quotes for strings, up to you. Here, sum. So here, that's my regular string. Now, if I can enclose in the square, I mean, not square, the curly braces, any type of variable outside the string. Now, this is going to be useful for those who want to, change, they want to see or print values. So you can use an F string with that. You can do the format function. That's completely fine. But in this case, let's just use the F string. So x plus y. So I'm going to see, it's going to let you see that the sum would be equal to x plus y right here. I'm just going to run this. And you can see it changes. So it prints the actual values. So we can change the values right here, maybe 8, not 80, let's do 75. So it's going to change, and voila. So you can continuously run this. That's going to be fine. Just again, take note that this is not the only program that's running. So if you have other variables that would, for example, use X, and you keep on running this, it might increment or decrement depending on what's your operation in the cell. So you gotta worry. Yeah, not worry. Gotta watch out for that, or you can watch out for the values right here. Okay, the shapes. Here you can see the values if you extend it a bit. Okay, cool. So always watch out for that. Let's have some logical operations. Very important if you're going to do conditions. So let's have three bools. We have bool 1 and bool 2. It can be a true or a false. Now, bool 3 would be an operation, an a comparator or equality check. So is bool 1 equal to bool 2? Okay. So take note that the double equal sign would denote equality. Okay. So is bool 1 equal to bool 2? Let's see. So is true equals to false? False. No. Yeah. So we just see the values here. So is true equals to false? No, it's not true. So let's make it true. So is true equal to true? Yeah, that's true. Cool. So yeah, that's easy. You can do other things, but again, we can do an and or operation. But again, you can try that on your own. Next is condition. So the input for a condition would be a Boolean operation or a Boolean value. So if any condition is met, then it will do the consequent, or rather the then clause. So in Python, how do we do that? So let's try to check values right here. So I am going to check uh is my grade over the passing. Let's say the passing grade is 70. So I'm going to run this. Oh, by the way, there's a new function input. So it's going to prompt an input in the display here. So I can say my grade is 80. I'll press enter and you get true, since the grade is greater than or equal to 70. Cool. Let's try it again. So let's say my grade is 65. Oh, 65. Press enter. So what's happened here is my grade did not pass since my grade is less than 70. So it's false. Now we take is pass as part of the condition. So let's see. So if is pass, so if I pass using, my pass is pass here holds the value whether I pass or not, given the criteria grade is equal to passing. Cool. Now, if I do pass, then I'll print a congratulations or congratulatory speech or whatever. And else would be if I did not pass, what would be the consequent or what will happen if I did not pass? Then probably I'll say, yeah, try your best. Try again next time. Let's try to do that. So I did not win. So I did fail on the last try I did here. So it says try again. So here's the non-continuity I'm talking about. So it's not, you have continuity when you're running rather. So here, let's run a condition. So let's do a new grade. So it's going to overwrite the failing grade I had earlier. So I'm going to run 90 here. And if I run it again, it's now going to change since the value of is pass did change when I run this again. Okay. So you need to watch out again if the values are changing. So these would depend to one another. Okay, cool. So next we do have a bit of a more complex variable, which are collections. Now I'm going to zoom in a bit for those who can't see. So collections are container data types. That means you have collection of different variables or different type of data that you want grouped together. Now we have a lot to do here, a lot of data types. We have lists, we have sets, tuples, dictionaries, frozen sets, and so much more. But we're going to talk about a bit of a few. So just lists, sets, tuples, and dictionaries. And we're going to do a bit of a fast introduction about them. Okay. So first, a list. A list is an iterable. That means you can iterate over the values, and it's a collection. That means it could be a collection of strings or numbers or whatever. So here I have a list of numbers, which is 1, 2, and 3. So these are a list of floats or list of decimals. A binary list could be, a collection of binary values or Boolean. So we have true, false, true. Okay. I'm just going to store this. And then since these are a bit of a collection, that means we can get data, put data, or even delete data. So to access a list, we have what we call indexing. So that means we can call something inside a collection by calling it out. So an indexing here, that means each of these numbers or each of these values inside the list has a corresponding ID or what we call an index. So here in Python, we do start with 0. So in MATLAB, you do start with 1. So that's a bit of a change. So this one right here from left to right would be progressing from 0 to n. That means the last or the length of the list. So this is going to be your first variable, first value, second value, and third. So those are indexed as 0, 1, and 2 respectively. So if we want to access number 1 right here, we need to get or use the square braces and indicate the index number, which is 0. Okay. If we put 1, it's going to print out 2 and 3. Oops, there's no 3. Why is that? Because we only have 0, 1, 2. Your size may be free, but the index, the last index would always be n minus 1. So in this case, there's no 3. That's why there's an error list index out of range. So we are going to have 2 to have the last thing. Now, what if I want to have a more complex or more flexible code that would get the last digit or the last value in a collection? What you're going to do is put a -1, okay? And that would always give you the last value of a list or a collection. So I'm going to add another one. Let's have a 5, 0, and a 6.0. 6.0. So if I do 3, so I'm going to run this. See, although I edited the list, it did not reflect right away because I failed to run this. Oh, now, if I run this again, this should now fix the problem. And now we have a 5. Cool. But again, we want to have a more dynamic code that always gets that gets the last index or the last value using the last index. So we have a -1, and this would always print out 6. Okay, or whatever last. Let's have another one, 9.0. Run this again, run this again, we get a 9. So yeah, -1. That's something that you might need to be familiar with. There's also with the bin list, but yeah, it's not really much interesting. But anyway, we're going to do some modifications. Now, let's use the bin list as a modification routine. So what if I want to change this middle value false into true? Now, we can find, let's identify what's the index of that value. Let's say it's 101. And we're just going to say equals to true. That means this is an assignment. So we're going to assign the value true to the bin list index of 1. And then we're just going to print this and see this is the new value of the binary list or the bin list. So it becomes true to true. Cool. Now, let's go to the next one, which would now be a tuple. Now, a tuple is a bit the same with the list. It's iterable, it's a collection. However, the tuple is non-editable. That means you cannot modify things in the tuple instead of a list. So here, instead of a square brace, you can declare a tuple using a parentheses. Okay, like this. So we have 237 XYZ. Let's say they are the fixed coordinates of something. So maybe we have an XYZ plane. So this is 237. And cool. Now we have num and tuple right here. We have declared that. Now I'm just going to run this. Okay. So the first item in the tuple is this. Last item is that. Same thing. You add an item, you can create a new tuple, add them together. That's cool. And oh, this is something new. This is what we call a multiple indexing. That means you're gonna get a range of values. So don't worry about that. So here, a left tuple will have from the original tuple right here, from 0 to 2, and the right tuple would be free uh, to somewhere. Okay, I'm going to make it a bit simpler for you. So let's have several tuples right here. Let's have T0 would be equal to 1, 2, 3. Okay, and I'm just going to show you. Oh, let's have more values, 4, 5, and 6. I'm going to show you how you can get multiple values or a subset within a collection. Right. So T0 is equal to, we index. So T00, that's index 0, you get a 1. Now, what if I want to get a range from 1 to 3? So that is from the zeroth, first and second tuple. So we can do colon, that means it indicates from to, you want 3. So you might be tempted to put a number 2 here since that's the index, right? No, that's not going to happen. So if we try to do this, we get only 1 and 2 because there's a Python syntax that you only you end before index number 2. Okay, so you need to include you need to say 0 until before the index 3. Okay, so that we can get 1 to 3. Okay, cool. Now we can also get from a middle value until to the last. So let's say I want to get here. So 0, 1, 2, and 3. So I want to start with 3 until the very last one. So I'm going to just press this. So this is going to be from 4, 5 until 6. So it prints from the third until to the last value within the tuple. This can also work with lists, by the way. So that's okay if you want to try it. So you can merge them together. That's what this one is telling us right here. Okay. So let's simplify that. But again, this is a bit of advanced. If it's a bit advanced for you, that's completely fine. You can always try it, again and again, or even search other materials. Again, cool. If it's okay, I think we can proceed. So, oh, by the way, you cannot modify tuples. So if I have a tuple right here, let's say I want to change number 3 to, let's say, a number 6. So number three is the second, as a second index. I want to change that to, let's say, a six. And this would throw an error since item assignment or modification is not allowed in tuples. So if you want to protect, or let's say have a fixed value for your tuple, fixed value for a collection, you may want to make it as a tuple. If you want to edit it, you can turn it into a list. Okay, so let's just exit this error. Let's not mind it for now. The next one is a set. Now, a set is a bit of a different type of collection. It's not iterable, but you can store values with it. So just like a regular set, so it will not support duplicates. So let's say I have this num set 1, 3, 4, 5. Then cool, it's gonna print 1, 3, 4, 5. Just gonna indicate that your set has a curly brace. Now, if I say I have 5, 5, 5, 5, 5 right here, you might expect that it's also going to print 5, but a set does not allow that. So it's just going to take unique values, 1, 3, 4, 5. Now, this is something that might be very useful for um, tests. Let's say if you want to have, you want to check unique values of categorical value of variables or values within a test or experiment. This is something useful. So let's say I have a result. Let's say these are results for, let's say, an experiment that I did. So you have success, marginal success, fail, marginal success. Now I want to see what are the unique variables right here. So I'm going to just see that. So in a list, so the original list is my results. Success, marginal, yes, yes, yes. And if I convert my list into a set, it turns into fail, success, marginal. So these are the unique values. Now, where could this be useful as well? If you want to find if there are faults with encoding of data. So what if I said I have success space? Okay. So you might say, in our perspective, this will not be much of a problem. Success is success. But if you run this, you can see that there is a duplicate of success. Now, in our eyes, it might be okay, but let's say if you're a data analyst or working with multiple data, this is something what we call a dirty input. So this is an anomaly in your data. So you might need to work on this. So even though there's a space, it's still considered as a different it's considered a unique value for Python or any type of language actually. So you might need to do some processing about this, but this is a simple way to check if what are your unique values in your data set. Cool. Next would be a dictionary. So a dictionary is one of the powerful collections that you have in Python. So a dictionary is enclosed in curly braces, just like a set. But the only difference is that you need to have key value pairs. So what does that mean? So if a key indicates what would be a non-numerical, just like a non-numerical identifier for a certain set of variables or a certain value. So key, sorry, just zoom in. So a key, again, would um, indicate, for example, an identifier for a certain value. So key, again, certain value. So if I would want to access a certain value in the dictionary, I can just set or call it using the key. So let's have a more intuitive example. So let's say I have a dictionary of charges for let's say I have an experiment using different, let's say, charges in your in electronics. Okay. So I have encodings of positive is equal to 1, negative is equal to -1, and a neutral is 0. So these probably something that you have came up with. So if we want to get a charge from the dictionary, I want to get a positive. So I want to get the value 1 using the code I have positive. I could get negative by just typing this key. Now this is a key. Again, this is the value. So I could just call using my key to retrieve a certain value. Now, why did I say dictionary is a powerful tool? It's actually a catch if you are, if you're familiar with C++ and you're very fond of using the case switch block. We don't have that in Python. sadly. But you do have dictionaries. So we utilize dictionaries to bridge that logical operational gap without case switches. We use a dictionary instead. Or you can use dictionaries to encode values. Okay. So let's say, okay, let's have, I have points here. So my key values would be, let's say, a point in space, A, B, and C, and they could contain coordinates such as 1, 2, -2, 0, or whatnot. So if I run this, let's say point A is this, point B is -2, 0, and point C is this, right? Now, again, I'm sorry if this is something too shallow for most of you or some of you, or too fast for the beginners. But then again, this is something you can work on it for many times and repeatedly. Again, this takes practice. If you don't get it right away, it's okay. So, yeah. But again, if you have any questions, you can contact us after the talk and we can help you with that. Great. Arrays and vectors. Now, arrays and vectors are very interesting data types right here. They are, I think you're familiar, of course, in mathematics, that vectors are a collection of specific numerical values. It could be represented, let's say, a 1D or 2D space. So we can try to look at that. So I think we already discussed this a bit. Okay. So to work with this, we do have a library in Python called NumPy. So NumPy is numerical Python. Its specific use is for vector analysis, linear algebra, or matrix algebra. So we're just going to import this. You can use import NumPy. Okay, you can end with that. That's going to work as well. But we're going to abbreviate that as NP, so it's easier to type. So this is an abbreviation or a mnemonic that you could use when importing a module. So I'm going to import NumPy with the name NP. So I'm going to utilize all NumPy using a nickname NP. Okay. So let's say I have a ball. Okay. A ball is maybe existing in a three-dimensional space. And these are, let's say, the coordinates in X, Y, and Z. I can declare an array or a vector using an np.array. And inside that is a list of numbers. So 1, 2, and 3. Now, this would indicate a one-dimensional matrix. That's cool. Now, you might argue this is going to be, we want it to be two-dimensional. Don't worry, we're going to get to that. So if we're going to declare two balls in a 3D space, we had one is in 1, 2, 3, X, Y, Z, another one is 0, 1, -1. And that's cool. Those are two different things. Now, if we want to encode them in a single system, let's say now we have two one dimensions and we want to merge them into one matrix, or already given the answer, you want to merge them into one system, we are now going to encode them into a matrix. Now, just like the same with the idea of vectors, so if you have two one dimensions of vectors grouped together in a, let's say, another vector, that will now give you a matrix. Okay, so an NP array of two vectors will give you a matrix. Okay, so we're going to print that for later. Now, this pool right here, okay, let's say the pool of values of the balls, we can now print several attributes. Okay, we have a shape, the size, a shape of a matrix, a size of a vector or matrix, whatever, and the number of dimensions, the dimensionality of the vector. Okay, so we're going to run that. So let's see. The size of the pool is 2, 3. Say the size of the array is 6, and the dimension is 2. Now let's try to look individually. What are those vectors? So ball 1 is 1, 2, 3, and the shape of the ball 1 is 3. So this is something that you would notice. If it's a one-dimensional vector, it's a 3 comma. So it has 3 elements for one dimensions. That's also the same with ball 2. If you want to print that, so it's going to be 0, 1, -1. Then if you want to see pool, you can see those are arranged now as rows. Okay. If you want to check the shape, so that's 2, 3. We have 2 rows and 3 columns for each of the rows, or 3 elements for each row. Okay. Then if you want to check the size, it's going to be 6, because this size attribute tells us these are how many elements are there in the vector or matrix. And the endim was about the dimensionality here. So it's now it's existing in a 2D ranked 2D. Okay. Right. So we can now work with iterations. Okay. So these are some of the things that we are going to work with collections. So iterations are activities in Python that loops around things. I'm going to speed up things. So I'm sorry for those who are, having a hard time getting this. But for the aspect of time, I'm gonna do a bit of a speed up. Okay. So let's have a list here. Hello, everyone. This again, a collection of words. Now, for item in my list, so for every object or value in a list, I'm going to, or every iteration, iterable or collection I have here, I could print that. Okay. So for every item in my list, so every item is hello, everyone, I am Dylan. So I'm going to print that every time. Okay. So I can change this, let's say, for every item in my list. Let's have another one. Let's have another one. So let's say I have, let's say, int list of 0, 1, 2, -1, -2. So I'm going to do uh, for num in int list. I'm going to print, oops, sorry, int list. I'm just going to print that for no. So it's going to print all of those values. Now, what if I want to take the cumulative sum or the sum of every value? So I might need to create another list for that. So let's say I have here, let's say, cumulative sum equal to maybe a blank. Okay. So let's say for the first item that we're going to store is 0 plus 1. Next to that is 0 plus 1 plus 1 plus 2 and plus -1 and plus -2. So we're going to do a cumulative sum for those. Right. So let's try to do that. So for num in int list, would that work? Let's see. So we did print this. Is that going to be okay? So let's try to do um, cumulative sum append. That means we're going to add it to the list, the current number. Okay. So let's see what will happen. It's just adding it. It's just adding the values. Now we want to add those values individually. So how do we do that? So one way to do that is let's try to take every sum of what's inside the cumulative sum. So if um, okay, I'm going to check first if the cumulative sum is empty because I want to take the sum, but you cannot take a sum of an empty set, right? Or empty, empty variable. So if the length of the cumulative sum is less than 0, oh, rather it's greater than 0, we are going to do something. So we are going to take the sum of the cumulative sum. Okay, how do we do that? So, okay, let's do cumulative sum of cumulative sum. Yeah, cool. So let's print. Okay. So now nothing's going to happen. So we need to store the value. So if it's greater than 0, let's add so 0 int list. So we have num. Okay. Put num here. It's just for sanity check. Okay. So it did not print anything since, okay, if greater than 0, Oops, sorry. So I think we're losing a bit of time here. So I'm sorry if I'm not gonna solve this right away. But if you can do this, it's gonna be something of your what you can do an activity. But don't worry, I'm gonna show this in a bit of the easier task later on, since this is gonna be a bit of a strenuous task, especially if you have bigger numbers. So I'm gonna show you a bit of an easier way to do that. Okay. So we can just add a list of numbers here. Oh wait, I'm gonna put that here. So we have int list here, and I could just convert this as an array. So I can turn this into, let's say, a vector of int. Okay. So we have np as array. I'm going to convert this int list. Okay, let's pick up int. Okay, so we have converted the integer into an array. Now, if you want to take the cumulative sum, or let's say just the whole sum of the vector int, we can just use sum. So it's 0. So yeah, it's going to be 0. So that's an easier way to take the sum of your vector. Okay. So to do a cumulative sum, you do some iterations of that. So this is a shortcut that we could do. Right. So next would be functions. So a function is a piece of code that you can store specific, routines that you do, logical operations or arithmetic operations. Okay. So let's say I want to store, a oh, I'm going to do a very simple first. So we declare a function using a def, and we're going to name that function. Let's say square. So this one, I want to square a value every time. So I want to square a value of x. Okay. And I need to do an operation, of course. So I'm going to do a square value. Let's say square value of that x. So how do we do it? How do we do a square? So maybe in C++, you're going to do a POW. In this case, you can just use a double asterisk 2 that will indicate x raised to 2. So that's a square. And we're going to return a square value. Okay. Let's run this. And I'm just going to add something here. So we can do a square of 2. There's a 4, 16, let's have a 5, 25. So that is a function. Now you can create more sophisticated functions if you want. Sometimes you don't have to want to return a return value. That's okay. If you want to just, do something or print something or display something. If you don't want to return something, that's also okay. You can also have functions that doesn't have any parameters. That's also cool. Cool. Um, there's a shorthand function called a lambda function. So why do we use lambda? One is to reduce space and to reuse functions within functions. So a lambda function is as such. So this is like a square. So instead of def square x, instead of that, this would be the syntax would be lambda x. X would be your input parameter, and colon would be indicating what would be the return value slash operation. So instead of a, it's going to be x. So this would give you the same result. So instead of x, let's name it as square or sqr. It's going to return an error because I removed that. So I'm going to do sqr. Okay. Oh, yeah. So it's implementing the same thing as this one. So if your functions could be very simplistic or very simplistic, you can turn them into Lambda function, especially if you're trying to model equations. So that will be easier for you. For example, if you're working on optimization, there's something that you might use for encoding your equations to do some optimization functions, right? Or I can do complex or multiple operations at the same time. This is an example that doesn't return any value. So in this case, I have two variables or two parameters, and I can just perform the different operations. So it's the same thing that we did earlier. So I have 10 and 12, and it's automatically going to print what are the sum, differences, the product, and the quotient of them. Okay, so cool. This is okay. Okay, so let's try a bit of exercise here For example, if you're doing maths and you want to encode it in Python. So let's do f of x is equal to x squared 2x plus 1. I'm going to use a lambda function for this. So f would be equal to lambda x. So that's f of x right now. And this colon indicates the equal. So I'm going to do x squared, okay, plus 2 times x. So remember to have the times here, plus 1. So that is my function f. So let's say f of x or f of x is equal to 1 or f or x is equal to 1. So this would be 1, 2, 4. It's going to be 5. Oh, so 4. Oh, yeah, sorry, 4. So yeah, it's going to be 4. So get a 2 here. It's going to be 9 for 2 plus 1. Okay, next, let's try a g. So the g could be encoded as lambda x 2 times x minus 4. So g, let's say g1 again here. So it's going to be -2. Okay. Or if we have 2, it's going to be 0. Okay. Cool. Cool, cool, cool. So we have now saved these two. Now you can do an f of g. This is a very good implementation. If you're using lambda functions, you can do f of g. Now you can encode them individually. So this is going to be 2 times x, let's parentheses, 2 times x minus 4 raised to 2 plus 2 times x minus 4 plus 1. Now you can encode it like that, but if you have very complex functions, I don't advise you to just do it easy like that or directly like that. F of g could be f of g of x. Simply as that. So if we would try to run a 2, so we get 1. So 2 times, yeah, you can just go through the math and that's going to be correct. So f of g is something like this, or you can do g of x or g of f. It's going to be simpler as that. So it's easier for you to run your functions as this. Okay, cool. Okay, we're now going to one of the exciting parts, which is vectorization. So we did introduce you to NumPy earlier, but now let's go deeper in how does it work. All right, so the NumPy right here would be, okay, I'm going to import it again. And now we're going to work with vectors, matrices, and tensors. Now, for some of you, these might be similar terms, some will be different. So let's see. Right. So we have scalar, vectors, matrices, and tensors. So let's start with a scalar first. This is one consideration that we have. So a scalar is just something, let's say A is equal to NP array of, let's say, 1. A is 1. So that's just a scalar value. Okay. So if you want to put a parenthesis or rather a square braces around it, that's also going to be okay. Okay. So, but still, this is now considered a one-dimensional array, but best practice is going to be, it should be here. If you really want it to be a scalar, you can put NP array or just simply, okay, just simply a scalar value like this. Okay, cool. So just like I said earlier, a collection of your scalars would be a vector, collection of your vectors would be a matrix, and collection of your matrix could be a tensor in the computer science sense. Okay. So in this case, if we are going to declare, let me delete this, going to declare a 1D array of 4 free vector A and B, but something like this, it's going to be okay, right? So these are now one-dimensional vectors, 4 free and 2 -5. Cool. Now, a collection of your vectors could be a matrix, again, if you combine them together. So we have A, B here, like we did earlier, and we get 4 free, 2 -5. Now, what if you want to declare them on your own? So we can have, for example, matrix X would be equal to NP dot array, parentheses, square braces, and I'm now going to declare each row. So we can do 0, 1, comma, second row, 1, 0. Cool. So this would be X 0, 1, 1, 0. Cool. All right. So this is how would you declare. You can even declare more if you want. So if you want to do 0, 0, 1. Let's have another one here. We have 0, 1, comma 0. And lastly, let's have 1, 0, 0. For an X there, we get this matrix right here. And that's cool. Now you can make your own and try a lot of different operations. Now you can even make a tensor. So like I said earlier, if you want to have combinations of your matrices, that's going to be okay. So I'm going to revert it to its two-dimensional form. I mean, in the 2 by 2 matrix form, and get this. Now, what if I want to have collections of these x's? So we have np.array of x, comma x, comma x. Okay, let's print that. What's going to happen? So it's going to be a collection of those individual 2D matrices. And if we check the shape of this, it's going to be 3 by 2 by 2. This means I have three collection of matrices which they have 2 rows each, and each of those rows have 2 elements. So it's a 3 by 2 by 2 matrix, or 3 by 2 by 2 tensor. Okay, so for those who are working with higher dimension vectors with higher dimensionality, this is something that you might be looking into. Cool. Let's do a bit of a linear algebra operation here. Okay. Now you can work with different activities. I do have another notebook explaining more about linear algebra in a different notebook for the sake of time. But again, let's just do element-wise arithmetic. So we can do eager execution. What we say about eager execution, it is using just the regular PEMDAS or addition subtraction in Python. And functional method is you use a function in NumPy to work with that. So a plus b is an eager execution, and ab would be a functional. NP add ab is a functional method. Either way, it's going to return the same thing. Okay, so it's up to you if you want to use eager or the functional method. Again, but I think you're familiar with linear algebra. Element-wise arithmetic would require you to have the matrices to have the same shapes. Okay, so please watch out for that. The same with multiplication. Okay, we have a times b, multiply here, and you can do subtraction and so on. There's also what we call a broadcasting technique. So if we have a scalar 2, let's check a again. So a is 4 by 3. Now, if I want to broadcast a scalar, we'll be doing this. So I could broadcast these 2 times a, so I can have 8 by 8, 8, 6 here. So that's also possible. I could also do 1 plus a. Now, you might think this is mathematically impossible to do unless you have, are going to use a diagonal matrix here multiplied by the scalar to get a diagonal matrix, and then you add them. Or you can just create, you multiply another ones matrix by the scalar, you're going to add it to that. That's okay. That's okay in the mathematical sense. But in Python, they automatically adjust that. So broadcasting is a technique when you do addition or subtraction. It automatically does that diagonalization, not diagonalization, automatically aligns the matrix to the target size. So here, instead of having, this is 4, 3, right? It's going to be a 4. It's going to add 1 to each of the values already. So that's going to be cool. Great. Next would be the inner product. So I'm going to skip the math explanation here. I think for most of you guys would know what would be the inner product is. It's just the dot product or what. So let's say I have vector cx here. So I have 1, 2, 3, 0, negative 1, 0.5. So one way to get the inner product, of course, is just going to multiply each of those values, each of the values in the vectors, and add them together. That's the inner product. We don't have to do the math. Don't have to do the for loop there, so it's going to be fine. And we're just going to do np.inner cx, and that's going to give us negative 5. So if you can do the math, then that's going to be fine. Now, you can also have eager execution. The eager execution version of the np inner or np dot would be the @ sign. So c at x is also the same as c dot x. Okay, so let's run that, and it's going to be the same. Cool. Now, this is a very common practice or a very common example for inner products. So here we have computation of grades. So let's say I have for prelims, midterms, and finals, I would have these weights. Okay, it's going to form a linear combination, and if you want to run with that, so we're going to multiply each of those values, then take the sum. So that's just the weights times the grades, or the inner product between the weights and the grades, and that's going to be it. Okay, you can try other linear combinations if you want to get the inner product, and that's going to be cool. Next, determinants. So I know determinants are some things that you might have a hard time in doing by hand. And if you're using MATLAB, that's going to be also okay. In Python, we can also work with that. So let's say we have an array 8, 9.4, 7.5, and 6.4. I'm not going to go through the mathematical explanation and the direct translation of the algorithm. The point here is to make your lives easier anyway. So I'm going to use the np.linalg.det. That means the determinant of the current array or the current vector I have. I'm going to run that, and it's going to solve the determinant for me. So you don't have to worry about that. So use np.linalg.det, and that's going to be okay. Next will be the vector norm. Now, for those who want to find distances in your vector or find the norm of your vector, it's also going to be okay. It's going to be easy. So you can use np.linalg.norm, and automatically this will give you the Frobenius norm, or the Euclidean norm in this case. Okay, so we can run the norm of this array. So yeah, it's going to be at 15.79. So that's the norm of the vector. If you want to find out more what's a norm of a vector, you can check it out and probably in the several textbooks that we have in your algebra. But if you do already know that, this is how you would implement it in NumPy. Cool. So or if you want to do the very traditional way, so we can just use NP, the sum of the multiplying arrays. This is also the same as taking the inner product of itself and taking its square root. So that is the Euclidean norm. And it's going to be just the same. We can change our NP sum RR here to R at R. Oops, sorry. So R.R could not be, okay, in this case. Sorry. So NP squared and RR, you need to take the sum of that later on. Anyway, so this is that this. Okay, let's just do a bit of math again. So this is an example of a mean square error. Now we can use the logic of NumPy arrays in taking the mean square error of something. Okay, this is an MSE. So this is just the Euclidean or the Euclidean distance, the average Euclidean distance, or the distance of the errors or the residuals. Okay, yeah. Okay, so let's just encode some arrays here. Let's say we have y is equal to np.array of, let's say, 1, 0, 1, 1, 1, 0. Okay, and y hat would be np array of 1, 1, 1, 0, 0. Let's see, do you have the same size? 3, 6, 3, one more. Okay, so we can make sure that they have the same size. Let's check that. We have y, the length of y, or the shape of y. The shape 6, and let's do y hat. Okay, cool. Then we can perform this operation. Okay, so let's work on the y minus y hat. So y minus y hat. Instead of looping through everything, you can just use the concept of vectorization to take this as just the difference between two vectors. So that's easier. Now we can just automatically get the square. We can do the square of this operation right now. So we can do np square, and we take those values. Cool. Now we can take the sum and divide it by n, or we can just take the mean. Okay. Sorry. So that is an easy way to do the MSE or the mean square error. So NP square is the square of the residuals, which is y minus y hat. And instead of looping over to take the sum, we can do the means. You can use sum actually if you want to do the SSE. That's the sum. But instead, if you want, instead of dividing it by the length, you can just take the mean. And voila. So this is one encoding of translating this equation to this. Next, let's try to use this one. This is the cosine similarity. So the cosine similarity would be how two vectors are similar to each other. For those who are working with natural language processing, this might be very familiar. Okay, let's try to encode this. So vector v would be equal to np array of 1, 2, 3, 4. And u would be np dot array of 4, 0, negative 1, 1. Cool. Now let's try to do this. So we can do the numerator first, which is u. I'll take note that dot there is an inner product, so we're going to use at v, and we are going to divide it with the norm of u times the norm of v. Okay, so I'm just going to use this instead. I'm going to use numerator equal to uv, and the denominator is, okay, we're going to solve that. So np.learnalg.norm of u times np.learnalg.norm of v. And we are going to take the the quotient of this. So I can use np, let's say, similarity or cos sim is equal to numerator or np.div of numerator and the denominator. Okay, and let's look at cos sim. Oops, there's an error. So numpy has no attribute of div, so it's divide, sorry. Okay, so this is the cosine similarity of the two vectors. Now, what if I want to find the theta? So theta here, you can derive it by taking the inverse the arc cosine here. So let's do that. So instead of just the cosine similarity, we can do np arc cos, and this is the angle between them. Okay, cool. So this is theta. So just comment that. Great. So we can add more. What if we want to work with, let's say, matrix transformation or linear transformation? So let's say we have x here. So I'm just going to do a bit of latex here. X could be a matrix here. So begin. We can do a flip, for example. Okay, so that's a flip operator there. And let's say I have let's use a basis vector right here. So let's say we have very simple. Let's have v is equal to another matrix right here. Let's say 1, 0. And we want to have the transformation x. Okay. So we want to find, let's say, j is equal to that transformation of xv. Right, so how do we do this? First, we need to encode x. So x would be np.array of inside 0, 1, 1, 0. Yeah, we did this earlier, but it was overridden. So yeah, V would be NP array of, take note, this is a column vector. So we need to encode a column vector. So we can do it like this. So first would be just one row of a single value, 1, and second row, 0. So we can check X the shape is 2 by 2. Cool. V now would be 2 by 1. Okay. So if we're going to do some inner product, we make sure that the inner dimensions are the same. So that's why we did that. So if V would now be 1, 0, we expect it to flip, become 0, 1. So if we do X at V, it becomes 0, 1. So that's a flipper, or this X here is a flip operation, or a flip linear transformation. So J would be equal to X at V. And J again, just the same thing. Cool. Yeah, I hope that helps in your vector or linear algebra. So this is just a gist of what's the overview of linear algebra in Google Colab or Python. Now I'm going to go a bit of graphing right here. I think some of you might be very interested here, especially in checking results. We're going to use several libraries. We have matplotlib, Seaborn, and pandas. So matplotlib and Seaborn are plotting libraries for graphs. Pandas here is for data analysis. If you want to work with CSVs, Excels, or export them into Excels, especially for experimental results. We're going to run that. So let's say I do have an experiment here. I have a temperature experiment, let's say a machine, and I'm checking the current temperature given the time. So I have here my time t and the current values of temperature. So I could turn this, take note, this is a dictionary. So given the column temperature, so my column here would be analogous to my key, and the rows of that column would be the values. And this would be the time, this would be another column. Okay, so I'm just going to convert this into what we call a data frame. So a data frame is just like an Excel or a CSV that you can encode into, our Python notebook or Python. So if I run that, you can see here. So it's a temp, time, and these are the corresponding values. Okay. Now I could plot this. Okay, I could plot this so you can see what's the reaction. You'll see what is the visual analysis to this. So don't worry about the syntax. You can search about it in the internet. We're not going too much in this, but I'm going to show you how it's done. So just the figure size, set the figure. I'm going to plot it using this, set the title, the X and Y labels, grids, and show the figure. So this would be the X axis, and this would be the Y axis. So you can see here, for every time t, or given the seconds, I can see the temperature progression for each of those. Cool. Now, I could even plot the functions. For example, earlier, I have a lambda like this. So I can have a function f of x equals to x squared plus 2, and x here would be the range, or rather the range of values I'm going to input, or the range of x. Okay, so it would be this is what we call an A range. So I start with -2, end with 2, with each step of 0.1. So in the range of -2 to 2, I'm going to have each incremental values of 0.1. Okay, so you can check that if you want. Then I have y is equal to f of x. Okay, so that's my x, that's my y axis. I'm just going to plot my x and y. Okay, cool. And see here, I can plot my parabola. Right? Cool, 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 cool. Now you can even plot your g here, or f of g, and you can see what are the results. Okay, if you want, especially if you want to model your functions. Okay, what if we have numeric or not, or numeric categorical graphs? You have a mix of both. So let's say here I have another experimental design. So I have a design alternative of A, B, and C, and each of them would give me, let's say, an accuracy result. And we want to see what are the performances. So I'm just going to encode this into, let's say, a data frame. Okay. So here, from each alternative, I have the corresponding accuracy. And I can do what we call a categorical plot, or for those who are familiar with statistics, this is going to be a box and whisker plot. So here I'm going to use Seaborn categorical plot. The data I'm going to use is the experiment sheet I have, which is this. The X values would be the alternative column, and the Y values would be the accuracy column. Kind here just tells me that my categorical plot would be the box and whisker. Let's run that. And you can see here now the box and whisker plot of each alternative that you have. Okay, so for those who can't read box and whisker plot, so just take note that the lines like this would be your mean. Okay, these the colored ones are in the range of your standard deviation, and the other parts here are the rest of the quartiles. Now we don't have the diamonds here. If you do see diamonds at the ends or outside of your quartiles, those are outlier data points. But in this case, we don't have. So that's actually it. There's actually category plots. I didn't put in here because it's maybe too much of the data I would need. So, but in case that you can use a heat map. So SNS or Seaborn does has a heat map as well. So you can try to do that. Uh, just make sure that you have cross tabulations between your categorical data so that you can see the plots. Okay, cool. Again, if you have any questions, you can just talk to me beyond this engagement. So I'm going to go with some noteworthy techniques or some good applications that is great when you're doing scientific computation in Google Colab. So I'm just going to make a function right here, a linear trend. So don't mind the all the math here, but yeah, you can mind it as well. So here, this linear trend just creates random data according to a trend that or current slope that I want. And this slope, I'm just going to base it with whatever data that I have. And here is the number of points that I want to generate. And isneg will tell me it's going to be, or am I going to have a negative or positive slope? So yeah, just going to run this. Oh, here, I want to plot that. So I want to have 100 data points. I'm just going to take X and Y since those are the data sets I just want to have. I used an underscore here just to throw the variables off. I don't need them as of the moment. It's going to just clutter my memory if I'm going to save more variables. So I'm just going to say, I'm not going to have it right now. So I'm just going to have, underscores. Cool. Next, I want to plot that using a scatter plot. And actually, you can see it right now. You can see there's somehow a fan type of linear trend in this case. Cool. And here's another one. There's a good function is you want to create a 2D Gaussian distribution, especially for classification problems. So this is one way to do that. So I'm going to create a Gaussian using a centroid and the given covariance or the set covariance that I want. So I'm just going to set here a random seed. A random seed, by the way, just sets the randomness of your whatever random generator that you're going to use it for. So here, I'm just going to create a covariance matrix here that I'm going to use for setting my Gaussian distribution. And I can use NumPy's random multivariate normal to set or create the 2D Gaussian. So I'm just going to set the center and the covariance matrix right here. Then I'm just going to split this by X and Y so I can plot it easily. So here, C would indicate my mean or the center of my distribution, which would be 2, 0. And GXGY would be my X and Y of the 2D Gaussian. So I set the covariance at 0.7. I'm going to put it as scatter right here. You can see here a Gaussian distribution of 0.7. I could change this into 1, 0 or 0, 0. And that will center in 0, 0 right here. I could also change the covariance if I want it to be, a bit negative. So I'm going to turn it around. So it's going to be negative covariance of 0.7, or I want to decrease the covariance here to 0. And you can see, the variance going to a regular round distribution. Okay, it's up to you. You can use this in multiple ways. I usually create this dummy point, so I can test some machine learning algorithms. And yes, you can use machine learning here in Google Colab as well. So one here is a Pearson's correlation, very useful for those who wants to do statistics of your experiment. Yes, you can use it right away. You can use SPSS, of course, it's your choice. But again, in Python, you could also use it right here. So I'm going to skip that part. And yeah, you see, this part is just showing the correlation between this linear trend. And here it's just showing it's going to show the covariance matrix actually that we set earlier. So we set the covariance as 0.5. So if we try to get the um, the correlation, it's going to print out the covariance matrix for this 2D right here. Okay. So we're using core coef. So core coef is a correlation coefficient. So it's going to take all of the correlations given the variables that you have in the set. Okay, so in this case, I have x and y. So I'm in this one. So x here, the column is x. So the x here in the first column and the first row is x. So the correlation, of course, there would be 1. And this one would be the correlation between x and y. This will be y. This is x and y. This is y and x. So eventually they are actually the same in this point. Cool. So this is the covariance matrix. It will be expressed as this. Right. So I do have an example here of the who life expectancy developing data set. I could upload that. So let me try to find it in my file. But don't worry, it's going to take a bit of not much of a time here. Let me just find that. Mhm. Okay, I'm just gonna drag it from my files. Okay, and it's uploading, and see it's who life expectancy developing. So I can upload that using pandas. It's gonna read my CSV here, and you can see that these are data. So this would be life expectancy from the World Health Organization, just to see a bit of actual practice here, or actual use of the Pearson correlation using a real data set. Okay, so I'm going to print out the columns here. I can see these are all the columns I have: country, year, life expectancy, so on and so forth. I'm just going to do a bit of a data cleaning here. I'm going to drop the NAs, and I'm going to show you the correlation of each of those, each of the parameters that I have in this data set. So we can do the data set of the correlation of that data set, and I can show it with a heat map, just like I said earlier. So this one is a good representation of your correlations, and you can see if it's lighter, that means there is less correlation, and if it's darker in color, either red or blue, it's going to be it has higher correlation. So let's say we're trying to predict life expectancy. So what would be good parameters to say that these are correlated? What are the factors that are correlated to life expectancy? So we can see that we have this 0.68 that is the adult mortality. Yes, very intuitive. We also have negative 0.621 here. This would be indicating to the HIV and AIDS for the countries. What else? We have 65 and 67 here. This would be the income composition of the resources and schooling. So this is a good example of using just regular correlation with your data set. And this is also possible here in Google Colab. So we can check this. These are some of the good life expectancy predictors. So we have cropped that out. So we have zoomed in to those parameters, and we can do what we call a peer plot. I'm not going to run this because it's going to use a lot of time. So this is the sample. Now you can see not just the correlation now, but also the trend of the parameters. So their reaction. Let's say for the life expectancy with the income composition of resources, so you see a bit of a linear trend right here, and the negative trend here in the AIDS, and a bit of a polynomial trend here in the BMI. But you can also notice that there is a grouping right here. So this we can slightly expect that there is a binomial distribution at this point. So that's something that we can watch out for. You can do a bit of a data analysis with these. Cool. So you can use that data or similar data also to create,
Yeah.
to do multiple linear regression. So we can use least squares as one of the examples. Cool. So you can model it using this. Okay. So we can run this one. So here we can try to model the data. So we can use this normal equation using the pseudo inverse of the Moore-Penrose matrix. So we can solve for the least squares. So that's just this. And let's run this. So in this two first, these are the parameters of our linear regression or the least squares. And this last right here is the bias term. Okay, so we're just going to add a bias right here. Okay, cool. And we can also, if you don't want to model it as the normal equation, you can also try to just use the libraries of linear regression, just like in SPSS or what. So you can get that from sklearn or scikit-learn, and we can just use linear regression. Okay, so we can set x as this. So that will be our training set. And yeah, and we can now fit those values right here. So x will now be just like here. These are the features that we want. Y would be the life. This would be your life expectancy predictor, or rather, the life expectancy. So that's the target. So we're trying to predict whether they are going to have this. What's the life expectancy of a certain country given these parameters? Okay, cool. So in this case, we can just run linear regression, fit it using X and Y data. Run this, and let's print the coefficients. So here are the coefficients of each of the parameters. We have four. We have your BMI, we have what else? AIDS, composition of resources, and schooling. And the last one, and schooling, this one. And here is the intercept, which is 47.415. This is the same as the last one right here. So it's technically the same thing. So you can just use linear regression or even more. You can check out the sklearn library if you want, and it's gonna have a lot of applications. There's ranging from support vector machines, logistic regression, random forest, and decision trees, and so much more. And if you want to run neural networks, it's not the topic covered here, but you can also run it in, of course, Google Colab. So again, these are some of the sources that you might want to look into, especially for those who want Monte Carlo simulations here. Then lastly, here are some references. All right. So I guess that's it for our discussion for
Thank you very
today.
much, Dylan. That's a really nice presentation. So, Asher, you there? Can probably go to the question and answer. Okay, so yeah, so that's the first question is coming from Lorena Villanueva. Hi, Dylan. This is really nice platform to let students make computations in the cloud. Would you like to? I would like to know if I can use this to run Java or C++.
Oh, sadly, we cannot use this for Java or C++. Although you can try other cloud-based learning platforms, I think JetBrains, if you're familiar, has education suites that you can help students learn online, or you can integrate your lessons as well. But for Google Colab, it's really specific for Jupyter notebooks or
Mhm.
Python. So yeah.
Thank you. Next question. Oh, someone with my name is asking a question. So can I use Google Colab to run our commands, or is this only Python?
This is a bit of a tricky question. It's both yes and no. Normally, if you want to code natural R, you cannot actually use that. However, you can use, there are packages in Python that could convert R code to run in Python in Google Colab. Uh, but that's going to add a bit work into the
Mhm.
process, but it's possible. But it's just really hard.
Okay, thank you. Next question, please. Okay, so this is from Asher. Can we run native LaTeX commands here in Google Colab, or should we use a Python library to make it work?
Um, I think when the difference of the actual LaTeX that we're using and the one in Google Colab is only for display. So the basic mathematics that you can use or displays in LaTeX could be used in Google Colab, but not for advanced primitive LaTeX such as other libraries for, let's say, making presentations, importing of special mathematic representation figures. Yeah, we can't use that there in Colab or in Jupyter Notebook in general. It's only limited to the basic mathematic representation, images, and the basic text formatting.
Okay, thank you. This question. Oh, okay. So this was when you were creating a column vector. So that was just probably a comment. And you just transpose the column vector.
Oh
So how do you
yes,
transpose the column vector?
yeah. Actually, I think I missed that very important part in my presentation. So yes, you can transform vectors in generally Python. So for example, I would declare a column vector, let's say x, given a shape of 2, 1. I can use .t at the end of that vector
Dot
that will
D.
automatically transpose that into a 1, 2 matrix. Or you can use np.transpose with the vector as the parameter, and it will automatically transpose that vector.
Okay, thank you. Next question from Burns. Buena obra. So great coverage and systematic development of usage of Python for math, especially. So that's a comment.
Thank you, Sir
Okay.
Burns.
So another comment from Burns. I like the functions part, especially lambda. The linear algebra part, like how to convert the math expression to a Python code. Nice.
Yeah. So yeah, I really also like this kind of practice in Python for computational thinking as well, sir. So I think it's something that many of us or many of the students would try to develop so that they will see math as a more interesting thing, that you can
Yeah.
see the interactions, like what's really going on if you have more numbers, not just really deriving it. And you can eventually plot those equations that we have and easily make them, see them in visualizations. What are the reaction to different types of numbers? And that will eventually lead them to the idea of scientific computation and linear algebra and so much more. It's based on that fundamental ability of transforming mathematics to algorithms, to visualizations, and to processes.
Yeah. Next question, or do you have any other question? Okay, Masher, I need to learn NumPy after this. I think I will find this easier to learn than Excel.
Yes. Although there's something else I forgot to input here is SciPy. Now, for those who are in the field of
Said UI.
operational research, if you want to do, for example, mixed integer linear programming, quadratic programming, SciPy also helps you to work on optimization. Now, for those engineers working with signals, you can just run Fourier transform easily with one code, just like in MATLAB, also here in Python. It's a very useful thing to use, especially if you want to visualize signals. So that's another thing for those out there working on signal processing.
Nice. Okay, next question. Can we write multiple lines of lambda in Python, or is it only possible for functions?
Um, yes, you can only write one lines for Lambda because that's the purpose of Lambda functions is for one simplicity and ease of running. So it's actually best practice if you have a bit more complex code or a routine of computation, you put it in a function as a routine rather than a Lambda function specific for one type of activity. A good use case for a Lambda function is one is plotting. Two is for mapping values, let's say in a whole 10,000 line data set that you don't want to manually compute in Excel drag and drop. You can just use a
Yes.
Lambda function to automatically convert a custom conversion of, let's say, a column. You may be using a very specific function that you want. So that's a good or powerful way in using Lambda functions.
Thank you. Okay, Burns. I'd like to do quantum optics calculations here, even signal processing this way. Thanks, Burns,
Yeah.
for your comment. Anything else? Oh, Brian. So from Brian, sorry if I missed, but are there integrations with Google Circ quantum computing framework?
Yes. Given that this is Google Colab is by Google, so we can readily import Circ without installing. So that's a one. That's a plus here, and I do believe Qiskit is also available here readily. So that's something that's also great if you want to prototype some code with your friends. If you want to do some quantum computing.
Nice, thank you. Uh, Wait, from Asher, can you recommend good sources of data for experimentation? That's free of
Mm.
charge, just like your example, like life expectancy
Oh yeah, I have two. There's one that we often use here in grad school is our world in data. So
or
OWID.
world data.
So you can search that in GitHub. They have a lot of data, especially for COVID. There's also for energy, and also yeah, life expectancy. But if you want a wider range of data, you can search in Kaggle. That's of course one of the free ones. And if you're into a bit of engineering data, there is IEEE data port. So if
Okay,
let's say it's very specific, let's say for um, let's say substation data, there's also data for let's say image processing, very specific actions or very specific financial data. Some of them are uploaded in IEEE data port. So yeah, those are good
okay.
ways of replicating papers as well or practicing data.
Thank you very much once again, Dylan. So what you have given us here is actually timeless, because mathematics never goes out of style.
Mhm.
So yeah, so thank you everybody for attending our event. We hope you learned something which you can apply in your daily life. So the good thing about this is you can view this presentation in YouTube anytime. Uh, if you miss something, then you can just review it. And we would like to invite you as well to our group, One Quantum, uh, to help us evangelize quantum computing technology in the Philippines. Join us in Facebook or subscribe to our YouTube channel. So thank you once again, Dylan, and thank you everybody for attending. And have a nice evening. Thank you.
Thank
Thank
you,
you.
everyone.
Thank you, everyone.